Okay, so this is active filter design, lecture 42. In the last class, we looked at noise in active RC filters and said that one can expect the noise spectral density to peak at omega p. That's because in most practical approximations, the transition band happens to be coincident or very close at any rate to omega p, and it also happens that the highest Q biquad also kind of coincides, has also the highest center frequency, which means that when we put together the results we saw for a single biquad, where we saw that the gain from every noise source to the output has a peak, right. The gain from every noise source to the output is either low pass or band pass, as we saw last time, or a combination of the two, and both the low pass and band pass responses have large peaks at omega p, right. This means that the noise spectral density will peak at omega p, and the higher the quality factor, we saw that the higher the, the gain is q, right, which means that the gain for the noise spectral density will be q square, right. So there will be a significant peak in the noise spectral density at the band edge. Now, what do you think will happen when you have a band pass filter? Can you use the same intuition? And for a low pass filter, what we saw, if this was the frequency response, for example, how will the noise spectral density look? Something like perhaps something like this. Okay. Now, if you had a band pass filter, by the same analogy, what would you expect? What is similar? It will peak at. Yeah, so what a band pass filter will do, the spectral density will basically do this, right. So again, the highest Q, in a band pass system, you will find that generally all the biquads will have high Q, because it's just taking these low pass poles and moving them far away from the origin, which basically means that the quality factors of all the poles will be very high, right, and and some quality factors will be higher than others. So you will find that the noise spectral density looks something like this. Okay. The next minor point I wanted to, this lecture is just a whole bunch of minor points which I wanted to mention. Nothing, there is no big specific topic as such. The next minor point I wanted to mention was that of distortion. Let me take an example of a GMC, first order GMC filter. So distortion. Right. So let's take a first order So what is the transfer function of this character? One by 1 plus SC by GM. It's a first order. Okay. Now, what did we see when we were discussing the active implementation of a transconductor? Which element is going to be nonlinear? This character is going to be nonlinear. In other words, if I apply a sinusoidal tone here, the current that is being injected here is not only the sinusoid but also harmonics of the input voltage, right. Now this harmonic obviously goes into this network, and the output voltage which is developed will also have harmonic content, because some harmonic current is being pumped into an impedance. The impedance varies with frequency. So you would expect, since it's a linear network, if you put in a harmonic tone, you will get an output voltage which is also at the harmonic tone. The amplitude of the harmonic tone will depend on the impedance. So one thing that you can expect is that at very high frequency, right, the capacitor will suck up all the harmonic current and the output voltage will be will have relatively small harmonic content because the filter itself is filtering off the harmonics. And please note that when we talked about harmonic generation, we said everything is fully differential in practice. So the really the most important harmonic you need to deal with is the third order harmonic, right? The third harmonic will be at 3 times higher frequency than the fundamental. So for example, if you were trying to measure or figure out how linear this filter is, right? Does it make sense to put a tone at at the band edge? Yes, no? Why? So if omega naught is at the band edge, 3 omega naught is way out there, right? So even if the transconductor is distorting badly, all that harmonic has been attenuated significantly by the capacitor. Okay. All right. Now let's so therefore it doesn't make sense to put the tone quite close to the band edge if you are interested in finding the harmonic distortion of the in other words, when you're quoting the distortion of your filter, you shouldn't be putting the input tone at the band edge and say, okay, my distortion is like whatever 0.1%, right? It doesn't make sense because most of the distortion is getting cleaned up by the filter itself. Okay. Now in practice, how is this resistor going to be implemented? It is also going to be a transconductor fed back on itself as shown here. Correct? All right. So we understand that now if the input transconductor is nonlinear, it also follows that the transconductor which is used to realize a resistor by the same token should be just as nonlinear. Does it make sense? Correct? I mean, if it doesn't, then I would remove the first transconductor, use that transconductor as the main transconductor. You understand? Okay. Now, can you comment on? So clearly, putting a high frequency or tone near the band edge is out of question. Is not a not a within quotes honest thing to do. So then I say, okay, I will put a tone at very low frequency, so that all the harmonics fall within the pass band of the filter, so that the filter is now within quotes not filtering off any of its own harmonics. Correct? Now let's imagine, let's figure out what happens at a very low frequency tone. So the frequency is very low. Okay. Now what do you think happens to the output voltage? This is the output voltage. Very good. Okay. So I mean, when we say low frequency, what do we mean by low frequency? I mean, in other words, when we say low frequency, we basically mean that the reactive current through the capacitor is very small in relation to the current through the resistor, right? So if the current through the capacitor is extremely small, almost small enough to be neglected, right? Then let's see what happens. This, let's call this Vi, right? This is some function f of Vi. Ideally, it should be Gm times Vi if the transconductor was linear. Unfortunately, due to nonlinearities in the transconductor, the current is some function of Vi, where, as you have done in your assignments, a good assumption is often to use f to be Gm times Vi minus some G3 times Viq, right? So that's a good approximation as long as you're not driving the transconductor into saturation, right? Now this current obviously is not going through the capacitor. Why? I mean, by assumption. Okay. Now if this current is not going through the capacitor, where must it be going? It must be going here, right? So that means what is so what must the equation governing this node voltage to this current be? I mean, as far if we apply the nonlinear relation to this transconductor, then f of V out must be equal to whatever I which is flowing there, correct? Because it's the same kind of transconductor, right? The sign reversal has already been accounted for in the sign reversal of I. Please note that I is flowing into the transconductor now. Yes, all right. Now, so to solve for V out, what do we need to do? So f of V out is nothing but I, which happens to be equal to f of Vi, which means what? V out will be equal to Vi, right? F inverse of f of x, right, which is x itself. Is this clear? And that's because both the transconductors are implemented the same way, right? If you want a larger transconductor, all you do is simply put multiple transconductors in parallel, in which case the f of, I mean, if you wanted, if you had a different transconductor, all that will happen will be whatever, this will become alpha times whatever, making the transconductor the same is what gets you V out equal to Vi. Does that make sense? All right. So what is the moral of the story?
You should choose midway between the omega naught by 2.
No, what is this telling you? This is telling you that if you put in a very low frequency tone,
You are not going to get a function of the distortion.
because distortion also is again very, very low, simply because nonlinearity is getting cancelled, right? Because the load network is the inverse of the input current. You understand? And in spite of even if f was horribly nonlinear, simply because the inverse f inverse of f of x is x, no matter what f is, as long as it's 1 to 1, you find that the input is the same as the output, and again you could get conned into believing that the filter is extremely linear, even though it actually could be far from it. You understand? So putting in very low frequency inputs doesn't make sense. Putting in very high frequency inputs or inputs near the band edge also does not make sense, because the harmonics then are filtered out by the filtering network. So what makes sense is to put the input tone somewhere in the middle. Now the question is, where is the middle? There seems to be a lot of middle. Okay, like as I go on, pardon? Yeah, so the within quotes, a good place to put the input tone is to make sure that the input frequency is high, but if I go on making it too high, the harmonics start going out of the band. So what is the logical way place to put the input tone, such that the third harmonic, which is the dominant harmonic, lies at the band edge, right? So roughly a good tone test is to put so if I typically plot the third harmonic distortion, which is the amplitude of the third harmonic at the output divided by the fundamental at the output. Yes, if the passband gain is 1, then the fundamental at the input and the fundamental at the output will be the same amplitude, right? You will find that at DC it's very low. Let's say this is omega naught, this is the band edge, right? And then kind of peaks and kind of falls off again. Okay. This will roughly happen around omega by 3. Again, the details depend on the kind of filter that you are realizing, but what I wish to point out is that trying to prove that your filter is linear by putting in a very low frequency tone, right, or a very high frequency tone, are both not correct. Yeah, okay. So let's see what happens in a second order filter. Let me take this example. Okay. At low frequency, what is happening? First of all, this output is what kind of output? This is band pass. Okay. So at low frequency, this voltage doesn't swing at all, right? And in any case, there is no current to the capacitor. So there is no, this guy is not carrying any current at all. So what happens? All this current, if this is Vi, f of Vi, where is all this current flowing? It's flowing this way. Okay. So what must this be? Must be minus Vi, right? Because f of f inverse x. You understand? So the same thing holds even for the band pass. I mean for a higher order filter. Okay. So this is an important thing to bear in mind, because often you will find people quoting distortion at very low frequency, right? And you know, basically this is just speckmanship. You know, I can always choose a sweet spot in my filter and put in my tone and then show that, hey, look, this is great, right? But to be honest, you have to quote stuff in the at the roughly around omega naught by 3. It in fact turns out that for Butterworth filters, for example, if you plot distortion as a function of frequency, it will indeed kind of peak at omega naught by 3. Chebyshev also, if the ripple is small, you will kind of get stuff peaking at omega naught by 3, right? So that's in general a nice place to a good place to put the input tone, right? One aspect of measuring distortion is the following. As we discussed a while back when we were testing a filter, right? It's not that we have access to just the filter, but this is sitting inside a chip, and then there's, you need to put a buffer kind of thing, and then there's some there's a balloon, and then there's a cable going all the way to the test equipment. So one thing about distortion measurement, where again you could get conned, is the fact that this whole test setup will generally have some frequency response, correct? So the response, so even let's say the fundamental has some strength here and the third harmonic has some strength here, right? What you're measuring is the fundamental strength here and the third harmonic strength there, right? So the attenuation of the fundamental and the attenuation of the third harmonic will not be the same, right? So to accurately estimate the third harmonic distortion, you must account for the frequency response of the setup, right? For example, if the setup had very low pass behavior, right? I mean, we saw that the frequency response of the external path, that is the cables, all that stuff, didn't really matter, because we were able to account for all of that by having a dummy path and then measuring this path and that path and then divide one by the other, and we are able to get the filter response even when the response of all that path you know is terribly low pass, right? But that won't do for a, I mean that if you basically test using this kind of setup, then the attenuation of the third harmonic will be different from the attenuation of the fundamental, right? Which means that you must account for that attenuation when you quote the distortion, right? Another measure of distortion, as I discussed earlier on, is what is called intermodulation distortion. Does anybody remember what this is? So if I put in two closely spaced tones at f1 and f2, right, and if this goes to the third order nonlinearity, you will also get tones at I mean, the easy way to remember this is call this delta, then what will happen? you will get F1 minus delta and F2 plus delta. And delta is nothing but F2 minus F1. So, this will be 2F2 minus F1 and this will be 2F1 minus F2, correct. The ratio of this to this is called the intermodulation distortion, and this is since 2F of F2 minus F1 and 2F1 minus F2 are resulting from the third order nonlinearity, the suffix im3 is used, right. If you had fifth order nonlinearity, what do you think you will get? What all components do you think you will get close to F1 and F2? You will get fifth order nonlinearity will cause two other guys here. But since the fifth order nonlinearity will be much smaller than third order nonlinearity, right, unless you are really overdriving the system, you typically will not be able to see those two. You understand? Okay. Now, so one way of measuring the linearity of the filter is to keep putting two tones. This is called what is called the two tone test or the intermodulation test, right. So, you put in a fixed amplitude of the input. The input now comprises of two tones F1 and F2 which are closely spaced, and at the output you measure the ratio of the amplitudes at F1 to F1 minus delta or F2 plus delta, and you can move F1 and F2, the average of F1 and F2 you can move all the way from a very low value all the way to in even frequencies beyond the band edge, right. So, can you comment on the intermodulation distortion at very low frequencies? Why?
Proportional to 1 by
So, again there is nothing to think about. At very low frequencies, as we just saw, the output will be the same as the input because it is f of f inverse or f inverse of f of x type thing. So, V out will be equal to Vi, which basically means that it is a linear system if you as far as the at low frequencies. So, there will be no intermodulation distortion, it will be very low, right. Now, as you go on increasing the tones frequency, right, in other words, the average of F1 and F2 is going on increasing while keeping the separation between the two tones the same. What can you expect will happen to the intermodulation distortion?
keep increasing and then
It will keep increasing, okay, and then it will increase,
all the way till the band edge.
and then what happens?
And then it will start.
Why?
No, because both is almost the filtering is same for both, so it will keep some saturated.
No, the left and right will have different distortion.
Why?
One of them will be across.
Oh well, I mean then I'll fix that by making the spacing between F1 and F2 infinitely small, right? Yeah, if the spacing becomes too large, what you're saying is right, but if the spacing is chosen to be very small, right, then that effect will not be there. Okay. What do you think will happen to the intermodulation distortion?
Then it will be the same. It will keep increasing.
It will increase to some extent and then
Okay, it will increase. Why will it increase?
because now the third harmonic, the distortion frequencies which are coming in are not too far away from the frequency that you are
Yes. Okay.
exciting with. So So there won't be any filtering effect as such coming from.
That's okay, but why does the distortion have to increase with input frequency?
Capacitor will now carry the current.
The capacitor now start to carry current, which means that whatever current you inject, for example, in the first order filter that we saw in the very beginning of the class, some of that current is flowing through the capacitor, so this inverse stuff doesn't work quite well, right? Because the same current is not flowing through both the transconductors. Okay, all right. So as you can expect that as frequency increases, the capacitor current increases, so you would expect that this becomes less and less valid, which means that the intermodulation distortion should increase. Now, all nodes in the filter will typically have a maximum response around which frequency? Around omega naught, right? So, and the distortion is proportional to, all these transconductors which are nonlinear are injecting nonlinear currents, right, which is proportional to the input voltage, the whole cube, right. So, the maximum amount of harmonic they will inject, or the maximum amount of nonlinear components that they will inject will be at frequencies where their inputs are very large, and that happens around the band edge, which means that around the band edge the intermodulation will peak, distortion will peak. Beyond the band edge, what is happening? The filter is filtering stuff off, so the node voltages are decreasing, right, which means that the amount of nonlinear currents that these transconductors are injecting will also reduce.
So, but it's filtering both the tone and the extra.
No, the what I am talking about is it is indeed filtering the sum of the tones, right. So, if the two tones are at frequencies beyond the band edge, for example, the peak voltage swings at every node in the filter will all now start to decrease, right. If the peak swings at nodes in the filter decrease, then the nonlinear currents injected by the transconductors must also decrease because it is proportional.
It should be almost in the same ratio, sir. I mean, F1 and.
It's cubic, right. The fundamental is proportional to Vi, the distortion terms are proportional to Vi cube. You understand? So, for example, if I at the output of the filter at a particular set of frequencies F1 and F2, and if I plot amplitude on the x-axis, or if I plot log amplitude on the x-axis and log the fundamental at the output on the y-axis, what should I get if I vary the input amplitude, right, and measure the output fundamental? I plot log A versus log output of the fundamental component on the y-axis. What kind of curve should I get? Yes, Yogesh? At a single frequency, I am increasing input amplitude and measuring output fundamental amplitude. What should I get? It should be a straight line with a slope of what? This should be a slope of 1, correct. This log of amplitude versus, so the gain goes away, the gain just is moves the intercept. V out is k times V in, let's say. Log V out is log k plus log V in, so the slope will always be 1 even if the gain is not 1, right. So this is a nice way of getting rid of the gain. Okay. Now, what do you think will happen to the intermodulation components? All the intermodulation components are happening because the signal is beating with itself, right. So it's proportional to A cube, correct. So what will the strength of the third harmonic amplitude be? Log of the third harmonic amplitude must be proportional to A cube. So on the log plot it will be, the slope will be so let me be a little accurate and draw slope of line 1 or a line of slope 1, line of slope 3, something like this. Okay. All right. So as the input amplitude increases, right, what can you say about the intermodulation distortion? What is IM3? IM3 is the ratio of the fundamental to the intermodulation tone. This one is proportional to A, this is proportional to AQ, right. So the intermodulation distortion, which is the log of the intermodulation distortion, is nothing but this separation between these two lines, right. As the input increases by some amount, the fundamental goes up by the same amount, but the intermodulation distortion goes up by A cube. So this difference goes up by or goes down by A square. Okay. All right. So can you comment on the practical difficulty of measuring distortion versus measuring intermodulation? Do you think an intermodulation measurement would be more reliable or a distortion measurement would be more reliable? Why? What is the difficulty with measuring distortion?
So we'll have a frequency at very high. We'll have a frequency at high frequency component.
Yes.
So because of that, the rest of the circuit, the transfer function, will be impacted by that high frequency.
Okay. What about intermodulation?
Intermodulation, we have a control on what it is around that omega naught. So if we can design the rest of the circuitry to have a band higher than omega naught, then we'll not have it.
No. Please note that here the distortion components and the input components are so close that they will pass through the same transfer function regardless of what you do to it, right. So the output, I mean, from the output of the chip to the measurement equipment could be 2 kilometers long, right, but it is since the distortion components and the input tones are very close in frequency, it follows that whatever was the ratio here of the distortion to the fundamental, right, will be the same at the output also, right. So an intermodulation distortion measurement is a lot less prone to error because you now don't need to worry about the frequency response of the test setup, right. You understand? And so if you had two filters, one with something like this and another one where
How do we decide on the input amplitude?
I mean, you got to make sure that this line is lower than which line?
Fundamental.
Yeah. Okay. I mean, please note that it's impossible because even if the output is a square wave, the third harmonic will always be smaller than the fundamental. You understand, right? So, so as long as you don't overdrive the filter, you will find that this will be. You're only interested in these, you know, in principle you're only interested in these lines, right? You know that they're straight lines. So in principle you need only 2 points. In practice you'll have a few more points and then get a best fit straight line and move on. Okay. So if you had one filter like this and another one, when I did the intermodulation, gave me a plot like this, which do you think is more linear? The blue one is more linear, right? And this point, this hypothetical point where the two lines intersect, that is the line of slope 3 and the line of slope 1 will eventually intersect. Mathematically, if I just produce those lines, they will intersect at some point. Okay, please note that it's a fictitious point because in practice you will not be able to put in, I mean, you will never get a third harmonic which is same strength as the fundamental. So in principle it's a, I mean it is a hypothetical point, but the farther that point is along the x axis, the more linear the filter is. Okay. So I mean, and when two lines touch each other, one, I mean you can think of it as this line of slope 3 intercepting the slope 1 line. So this is often called the input intercept point, right? And because we are dealing with third harmonic distortion, third order intermodulation distortion, this point is called the IIP3, right? Input intercept point for third order nonlinearity. All right, you understand?
So what about for bandpass responses? There, I mean, almost all the frequencies are like high frequency.
No, that's why. So again, so when we now measure bandpass filters, right? This harmonic distortion doesn't make any sense at all, correct? Because you have a very narrow band filter, the harmonics will be, I mean, for example, let's say you have 2 gigahertz filter with a bandwidth of 10 megahertz, right? It doesn't make sense to do any distortion measurement at all, because you put 2 gigahertz, the third harmonic is at 6 gigahertz, which is like completely filtered off by the filter itself. Okay. So in such examples, harmonic distortion doesn't make any sense. The only relevant or rather a sane measure of nonlinearity is intermodulation distortion. So whenever you go into, for example, RF or wireless systems, nobody even talks about harmonic distortion. It's totally irrelevant, right? For the reasons I just mentioned. So all distortion is all measured using, all nonlinearity is quoted using intermodulation measurements, where you put in two closely spaced tones. That's easy to do, right? Even if you have a 10 megahertz bandwidth that centered at 2 gigahertz, I will choose, for example, 1.999 gigahertz and 2.001 gigahertz. So these are two tones, right, which are spaced 2 megahertz apart, right? So the intermodulation tones will also lie in the within the signal band, correct? And you can and they are not attenuated, so everything is.
If we make delta very small, it is effectively giving a single tone.
No, it is not. I mean, two tones are different. I mean, delta very small means that delta is very small. That's all.
How small can I make it?
You can make it arbitrarily small. It just mean that you have to wait for a very long time before you can make the measurement, right? See, what is fundamentally happening if you take two small two tones with amplitude A and what do you call frequency delta apart, then how long will it take for the amplitude to go to 2A? What is the maximum amplitude that you are putting into the filter? If you had two tones of amplitude A slightly separated in frequency, the maximum amplitude is 2A, correct? So the amount of time you need to wait to hit 2A is proportional to 1 by delta, right, which is the difference frequency, correct? So if you put in a very small tone spacing difference, then it will take a long time. Then the BTechs who have done the spectrum analyzer project in your lab, right? If you have to build a spectrum analyzer which is able to resolve two tones very close, then the bandpass filter which follows, the Q should be very, very high. A high Q filter means that it will take a long time for its output to settle, which means that measurement will take a much longer time. You understand? Okay. Then the last minor point I want to mention. This has got to do with your homework and nothing else. So in class we saw all these fixed GM bias circuits which were based on putting the delta V and then measuring I and then using a negative feedback loop to fix the transconductance. In the assignments we saw circuits of this kind. correct? And what are the dimensions, one set of dimensions which make this work? I mean, how many people recognize the circuit now? Everybody? Okay. If this is size x, what should this be? 4x. Y? Y. Okay. And what about this guy? If this is R, GM of which guy is 1 by R? Is 1 by R. Okay. All right. So this circuit we saw almost as take it type. This thing we analyze and then make sure that it is indeed 1 by R if square law is valid. Right. I'll show you that though it's not very apparent, this can be also derived very quite a straightforward manner from negative feedback principles. Right. So let's say you're in the lab, right, and you had a transistor. If you wanted, and it was carrying some bias current I, and there was some VGS, right, and I told you to measure, and it's a square law device. So in other words, I is some blah 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 into VGS minus VT the whole square. If you knew this, if you knew VGS and if you knew I, how will you figure out its transconductance? Pardon? So 2I by delta, right? In other words, if you knew the characteristic of the device, then you don't really, technically transconductance is delta I by delta ID by delta VGS for any arbitrary device. But in the special case that you have a square law behavior of this kind, then you don't need to make a small signal measurement, right? Just with a single point, because you know the curve, right, you measure I and then you do VGS minus VT, and the ratio of the two will give you something proportional to transconductance. Okay. Now given this background, if you wanted to tune, or if you, the question is what current should I pass through this device so that its transconductance is 1 by R. That is the question we want to ask, right, because we wanted to, okay. So how will I figure out in the lab, how will I figure out what current I must push into this transistor in order to get a transconductance 1 by R, given the discussion we just had?
Put an voltage across 1 by R resistor and see the current flowing and compare it with
So you say, okay, I am going to pump a current I to the device. This voltage will be some VGS, which is VT plus delta V. If 2I by delta V is equal to 1 by R, right, then if 2I by delta V is R, then I is the right current. If I is the answer, if 2I by delta V is less than 1 by R, what does this mean? This means that I is too low, I must increase it. On the other hand, if 2I by delta V is greater than 1 by R, it means that I is too high and I must decrease it, correct. So 2I by delta V being less than R is equivalent to saying I is less than delta V by 2R, correct. In other words, I should compare delta V by 2R with I, right. If delta V by 2R is too small, then what does it mean? If delta V by 2R is smaller than I, it means that, right, okay, alright. So this is VGS with VT plus delta V. So I need to generate delta V by 2R. Okay, so what do you think I can do? what is the most, I must subtract out Vt, right, and divide by, I mean generate delta V by R, right. So what kind of controlled source would this be? A voltage controlled current source where I need to subtract off Vt, right. So what is the topologically what is the voltage controlled current source that you know? The common drain type this thing, right. If this for example is infinite size, right, then what is this voltage? If the size of the transistor is infinite, then the gate source voltage will be Vt, alright. Okay. So now if this is Vt, what is the current through the 2R? This should be delta V by 2R, correct. I must compare this with, I must compare it with what? With I, correct. So okay, so this was I, this must also be I, correct. If this voltage is going up, it means what? I is more, which means what should I do? I must decrease I, correct, alright. On the other hand, if this voltage is going down, what should I do? I should increase I, okay. So both these, in other words, are tunable current sources, alright, okay, which are controlled by this potential. Does it make sense? So what are the what is the easiest tunable controlled source, current source that you know, which varies in relation to a voltage? Two PMOS transistors, both these currents must be identical, correct. Okay. Now if this goes high, what must happen to this node voltage? That should also be increased, right. So what happens, what do? You short these two, you understand, alright. So so this is one version of the fixed GM bias, right. Now the only problem with this circuit is that the transistor size must be infinite, right, alright. So then it doesn't take too long, I mean I guess once this is there, and you can now fool around with transistor sizes. I mean 1411 is not really, I mean is not necessarily the only way to do things, right. If this was X, this was Mx, and this was Y, and this was Ny, right, you will find that this will also servo. All these things are basically, they will not be servoing it to 1 by R, but some multiple of 1 by R, that's all, right. So that it still doesn't really matter as long as they are all proportional to 1 by R, you understand. So even though this looks, I mean it doesn't seem very obvious that there is negative feedback, the idea is actually